Alright, so let's talk about one of the coolest, most powerful ideas in all of data science, regression. We're going to go on a little journey here to see how some simple math becomes this amazing tool that can, well, kind of predict the future. It really all boils down to this one question humans have been asking forever. How can we know what's coming next? Whether you're talking about tomorrow's weather, next quarter's sales numbers, or where a stock price is headed, we all want to know what's around the corner. And it turns out the key isn't some crystal ball, it's data. And that right there is where regression steps onto the stage. At its heart, it's just a powerful way to find the hidden relationships in data we've already collected. Once we understand those connections from the past, we can make some seriously smart guesses. What's coming next? It's the engine behind so much of the prediction we see today. Okay, so how does this thing actually work under the hood? We're going to start with the simplest version, the absolute building block. You can really just think of it as connecting the dots. Just picture this. You've got a bunch of dots scattered on a graph. Let's say on one side you have hours studied and on the other you have test scores. The big idea here, the absolute core of simple regression, is just to draw one single straight line that best slices through that cloud of points. It's all about capturing the general trend. This line isn't just drawn anywhere, there's a method to the madness. And it's described by this classic equation. I know it might look a little scary, but stick with me. Every single piece has a really simple job. Let's break it down. So why that's the thing we want to predict, right? Or test score. X is the info we're using to predict it, the hours we studied. That beta 0, that's just our line's starting point. But the real magic, the most powerful part of this whole thing is beta 1. That's the slope. It tells us exactly how much our test score is likely to go up for every single extra hour we study. And that little epsilon guy at the end, that's just us admitting, hey, prediction is perfect. There's always going to be a little bit of error we can't explain. Okay, but wait a minute. This raises a really important question, doesn't it? I mean, you could draw a million different lines through those dots. So how on earth does a computer figure out which one is the absolute best one? I mean, it's a fantastic question, isn't it? How in the world does the algorithm pick that one perfect line? It's not magic, I promise. It's actually a really clever, logical way of measuring mistakes. The whole secret to this is a little thing called a residual. And all that is the distance between a real data point, what actually happened, and where our line predicted it would be. You can just think of them as the little leftover errors for every single data point. The process itself is actually brilliant in its simplicity. First, the machine looks at every single data point and measures that error. Second, it squares all those errors. This is a slick little math trick that makes sure all the errors are positive and really penalizes the big misses. And finally, it just keeps adjusting the line, nudging it up, down, changing the angle until it finds the one single line where the grand total of all those squared errors is as small as it can possibly get. And this total error score, it's got a fancy name, the cost function. In the entire game is to make that cost as tiny as possible. Find the line with the lowest cost and boom, you found your best fit. This super simple idea of minimizing a cost is at the very heart of pretty much all of machine learning. Alright, so straight lines are awesome, but let's be real, the world is messy. It's really that simple. So now we've got to upgrade our toolkit a bit to handle that real world complexity. I mean, just think about it for a second. Your test score isn't just about study hours, right? How much sleep you got or what your grades were like before. And a house price, it's not just about square footage. The neighborhood matters, its age matters, the number of bathrooms matters. Most things in life are a result of a bunch of different factors all working together. And that is exactly why we have multiple linear regression. It's the same core idea we've been talking about, but instead of just one X to predict our Y, we can throw in a bunch of them. It'll find the best relationship that balances the influence of the house size and the location and its age all at the same time to make the most accurate prediction it can. But hold on, there's another wrinkle here. What if the pattern in our data isn't a straight line at all? What if it's got curves and bends? Sticking a straight line through that would be, well, a pretty terrible fit. Well, for that, we've got another tool in our belt, polynomial regression. Think of it this way. If linear regression is for straight roads, polynomial regression is for the curvy, winding ones. It cleverly adds powers of x into the equation, which lets our line bend and twist and flex to capture much more complex patterns, like the curve of population growth, how temperatures change over the seasons, Okay, so this all sounds like pretty neat theory, but you might be asking, why should I care? Well, because this stuff is quietly running the world all around you every single day. Let's look at a few examples. Take sales forecasting. Businesses live and die by this. They are constantly using regression to figure out future sales by looking at how things like their ad budget, the time of year, and what the economy is doing are all connected. In finance, oh man, it's everywhere. Analysts are building these super complex regression models to try and predict stock prices, feeding them everything from market news to company profits, all just to get a slight edge. Even the electricity in your house, utility companies are using regression to predict exactly how much power we're all going to need, looking at things like the weather forecast and the time of day so they can keep the grid stable. And think about healthcare. It can even be used to estimate how long it might take a patient to recover based on things like their age, their specific condition, and the kind of treatment they get. The point is, this isn't just numbers on a page, because here's the thing, it doesn't matter how complicated the model gets. It could have one input or 1,000. It could be a straight line or a crazy curve. The core idea, the big takeaway, is always the same. You're just using what happened in the past to make a really good guess about the future. So there you have it. You now understand the fundamental logic behind one of the most important tools in data science. It's all about finding that best fit line, which really just leaves one last question for you to chew on. Now that you know the secret, what would you predict?